Great. All right, so this lecture is called Solving Image Geometries, or how do we find our extrinsics? We went through just before lunch, Jenna talked about the lens calibration, which gives us our intrinsic parameters. And so now we're going to talk about solving for our extrinsics, which is the camera's position and orientation. And that's how we relate the camera coordinate system to the world that we all live in. Okay. Yes, as this slide says, the extrinsic calibration provides us the information to align our world coordinate system, which is in yellow, and our camera coordinate system, which is in red. Okay, so again, this has different names that you might see in the literature. An extrinsic calibration, you may also see it called an exterior, these parameters called exterior parameters, or some people talk about this as camera geometry. It all sort of means the same thing. The extrinsic calibration finds the 6 coefficients that describe the location and viewing angles of a camera once you've installed it for a fixation, or as a function of time, if those extrinsics are changing through time, as if you were flying from a UAS. So those 6 coefficients again, or those 6 parameters that we need are the XYZ of the camera and the orientation, azimuth, tilt, and swing. Sometimes these can be difficult to measure. And so instead, if possible and when possible, we try to solve for these parameters using known features in the field of view of our camera. We call these known features ground control points, or GCPs. This is an example of Nick Spohr, who was in here earlier, and you'll all meet as part of the hands-on demo tomorrow, laying out a GCP on the beach. We typically use these large targets, the sort of a single black and white checkerboard. There are different types of targets out there, but this is typically the convention that we use. And then we go out and we precisely survey the location of those GCPs. So take-home points, you need to know your extrinsics to make maps with your images, and you need to recalculate them every time the camera moves, or use some sort of correction algorithm, which we'll talk a little bit about, to match features between images to remove that movement. All right, so back to our favorite equation, our camera projection equation. So specifically, we're going to be focusing on the rotation matrix and the translation matrix and how we get the parameters to fill those 2 matrices. All right, we saw this slide earlier. I messed it up. I'll try to do it correctly this time. So the terminology and the convention that CIRN tends to use is azimuth, tilt, and swing to define the orientation of your camera. So azimuth is the angle that the camera is pointing or looking. So that's, are you looking down the coast? Are you looking out to sea? Your tilt is your pitch. So that's how far up and down the camera is pointed. And then your swing is your roll. And as we said earlier, there's more information about these definitions and the rotation matrix construction in the user manual. Brittany, is there anything you think I should add about azimuth, tilt, and swing? Okay. All right. As we mentioned, it's very hard to measure this. You can try to sit up there with your phone and, or an IMU and try to get a measurement of where the camera is pointing and how it's tilted. But that's not going to be accurate enough for what we need to do. And so, again, we try to solve for these parameters. We do recommend, if you are going out and you're installing a camera somewhere, to try to measure your camera location, if at all possible. So stick a GPS right on top of your camera and get its location. And if you can try to jot down in your notes some estimate of your azimuth, tilt, and swing, that is also super helpful. The solvers that we are going to use do a much better job when you give them somewhat accurate guesses of what these parameters should be for them to start with. So again, take a GPS, get the location of your camera. If you are collecting your data from a UAV and you have a trajectory file that's telling you where your UAV was, you can also go into those data and try to pull out a location of that UAV. And that may also have, you know, the roll, pitch, or yaw of the UAV, and you can think about how that translates to where your camera is actually looking. Sometimes this information is in the EXIF data also, and you can extract that. Or, you know, if it's a fixed camera installation, you know, your smartphone might have an app or something where you can hold it up and tilt it, and it will tell you the angle. So that can be helpful for your tilt or your swing as well. So there's a few different ways to get these initial estimates of what these parameters are, and we'll use those as input guesses into our algorithm to solve for the extrinsic parameters.
Yeah. To make your life easier, it's usually I would use units and coordinate systems that you plan to be doing analysis in. So don't put Latin logs, it won't work. Put state plane meters or UTM or a projected coordinate system. If you start with the coordinate system you want, it'll just make things easier.
Yes.
What are we looking for in terms of the accuracy of the GPS measurements?
How accurate should your camera position be? Is that the question?
When you say that, go and take some.
For the targets, we like these to be as accurate as possible. So we typically use RTK or PPK GPS. So, you know, a few centimeters is what we're aiming for. In terms of the rough guess of where your camera's at, if you have RTK or PPK readily available, please use that. If you don't, then use whatever you have, and we'll, you know, use that as a starting point.
When you're taking the GPS out of the camera, often you can't be at the pinhole because you have to get the camera apart. So we would usually take a shot to the top of where we estimate the pinhole to be, which we think is about an inch back using imperial units from the front of the lens. So we would put the tip of the measuring rod there for a short thing, and then estimate the height difference in your vertical. And that will give you a pretty good estimate of the pinhole.
Yep, that's a really good point. You're never going to be able to measure exactly where it is. And so, you know, depending upon your camera and the form factor, sort of use your best judgment. Usually the manual gives you some information about where that is. Yes, Saunders?
I'm not sure if I'm confirmed finding the exact position of the camera, because most of your reference points pixel height is always way larger than a couple of centimeters. So the calibration itself, most times already have a problem with finding the position within maybe 10 centimeters. So it doesn't really matter that the camera is not calibrated, because pixel height of the area that you're using doesn't
It does depend on your setup, what, you know, a pixel size is for your GCP targets that are very, very far away. I would agree.
For the area that you're interested in the waves, pixel is already that large. A couple of centimeters doesn't really matter.
It typically is, yep. We try to be as accurate as possible as a starting point. All right, so now we have our known points in our image, and we basically need to find their pixel locations, which we do by looking for those known points in the image. And then we know their world points, the XYZs. So we have 6 total unknowns that we're solving for. So we need, at the very minimum, 3 known points to solve that system of equations. However, we prefer to have more than 3, and we use a nonlinear least squares solver to get a better estimate of those parameters. All right, so how do you get your known points? We talked a little bit about that. Our GCPs, visible points whose locations are known and whose image locations can be found. And so I think, this is somewhat what Saunders was talking about, is if you look some of these targets that are at far distances, a pixel is maybe on the order of the size of the GCP. And so it's more of an approximation than, some of the targets that are closer, you get many, many pixels on that target. And so you can find the center of that target very well. And within the toolbox, and Brittany's going to take you through this, the function is B GCP selection, and it goes through how to click the GCPs and store that data in your image. So again, we talked about how we want at least 3 to 4 ground control points. I almost always do at least 4. We talked a little bit previously about the spread of the GCPs across your image. So having only 4 GCPs in a single line would be a fairly poor setup for your GCP. These are some examples of a better and most optimal GCP distribution.
Since that you have one in the better and the best, that you have one that is in the splash zone,
I think that is trying to illustrate a point. You do not want your GCP somewhere that is going to move.
I guess my question is now, is it possible to run the GCP on a stick?
Yes. So when you are setting up your initial camera station, a way that you can get around having poor GCP distribution is if you have a boat, that's possible to be in your field of view, and you put you can put a GCP on a boat, and you can take a bunch of images of that boat as it zooms around within your field of view. And then you can you can composite that together into one image if you know your camera was not moving over the time that the boat was moving. And so you can sort of add these additional GCPs from multiple images to get information or to get a better spread. You can also, if you have a backpack and you have a GCP on a stick and you want to wade out into the swash zone safely, of course, following all of your universities or agency safety rules, you could do something like that. And then you sort of composite the image together to create a single image that includes as many GCPs as you can. All right. Yes, Meg?
I just wanted to say, we also use the composite image on a really busy beach where we don't want to leave the ground control points out for a long time.
Yeah, that's a good point. Because this bullet point down here, we recommend adding do not touch labels to your GCPs, because beachgoers walking on the beach, the first thing they do is they're like, oh, what is that? And they lift it up. Mm-hmm. And as soon as they've lifted up, it's now moved from either where you surveyed it or where you clicked it in your image. Yep.
Elevation.
Or sorry, the elevation of the GCP. I like to spread them as much as possible in elevation as well. So instead of having them all at the same elevation, sometimes that's not always possible.
But we try to project the plane from camera plane. So that original plane has to be on the same elevation.
No, so we just use the elevation of the GCPs to back calculate the position and orientation of the camera. Once you have those extrinsic parameters, then you can define whatever elevation you want for your grid points. So you can give them all the tide elevation or something like that. Does that make sense? So the elevation matters for the initial solution. And then when you go to define your grid points, you can redefine the elevation of what you're interested in. Does that answer your question, Hira?
Oh,
maybe. Okay. We can come, do you guys have anything to add to that?
Yeah, I think we're mixing a little bit of the rectification and the extrinsic solution
Yeah.
stuff. So I think in terms of extrinsic solution, what Kate was saying was we have GCPs at various elevations that really helps us figure out the tilt of the camera. And then, I think what Hiro was saying is when we actually do make a projection, what Kate was talking about when we specify our grid points and we pull it all back, we typically have to guess an elevation because we don't know every single elevation what we're looking at. So I think it'll be a little bit more clear once we get to the image rectification section. Because I think did you already show the equation? Because we'll show where everything fits in the equation in a couple of slides.
Yeah, we started with that and it'll come back. Yes, Rob.
If you have a special case where you've surveyed the camera, you've probably done it to within a few centimeters, then actually you're only solving for the angles. And you can use the bad choices and other choices.
We talk about that a little bit in a few slides. Yes, Saunders.
Remember, the new rectification of the camera, still have problems calibrating because it didn't have any reference to the point we need to see. It's meant that our image was illuminated. On the range much wider than the latest scanner. This will way to solve that if you don't have any uncomfortable points in part of the image.
So that's sort of what Rob was getting to, you want an image, you want a spread of GCPs like the one on the right. There are going to be cases where you cannot get something like that. And so we're going to talk through some things that you can try for some of those times when you cannot spread your GCPs like the one on the right. But in an ideal world, you try to spread your GCPs around your entire image. Okay, so we use the camera equation with the known points in our image to solve for our 6 unknown extrinsics, like we talked about. And so this is just telling you the parts of the toolbox that we do this in, and Brittany will take you through the practicum. So once in the toolbox, you click your GCPs, you enter your surveyed XYZ coordinates in your world coordinate system, whatever coordinate system you want to be working in. If you want to work in a local coordinate system, enter those in a local coordinate system. If you want to work in a world projected coordinate system, put them in that.
I would, for this particular toolbox, I would put them always in a geographical coordinate system.
No local coordinate system.
There's an option to make your own local system later. That way you can make many different local systems.
Okay.
But Kate is right, you can put it directly as a local system.
So use a world projected coordinate system here. And so it's the C part of the code, so single extrinsic solution helps us bring all these pieces together and solves for the extrinsics, and the function it's calling is the extrinsic solvers. So you see you put in your initial guess parameters, and then you put in if there are in any parameters that you want to fix that you think are known, like Rob was talking about, if you're super confident in your camera XYZ location, and we'll walk through that. You put in your intrinsics, and then you put in your UV coordinates of your GCPs and your XYZ world coordinates of your GCPs. Okay, so the question that we all have, what if you, and this is sort of saying, what if you have a reduced degrees of freedom, or you can't spread your GCPs in both dimensions, and you only can get a few points along the dune or beach in the lower portion of your image, for example? How can you use additional pieces of information to help? So you might be able to get the GPS information of the camera from a survey of the camera, like Rob said, or from the UAS trajectory itself, from the data available out of the autopilot. You can guess at some of the angles if you're collecting data from a UAV and it does has a super nice gimbal. and it keeps it nice and stable, and your horizon is nice and flat, you can say, oh, my roll is 0. And so there's a paper from 2016 that evaluated some of these questions and ran through some of these examples for data collected with an old DJI Phantom. And then we compared the estimated true ground positions. We compared the estimated and the true positions for the GCPs using these reduced degrees of freedom solutions to sort of demonstrate the scales of error. And this is just a table that is from that publication. And it goes through over here. It's telling you basically the parameters that we said were known and we held fixed. So this would be an example where we said, hey, we knew the exact position of the camera. We don't want you to solve for the position of the camera, only solve for azimuth, tilt, and roll. And so this is saying if you know the position of the camera, like Rob suggested, you can get away with maybe only 2 GCPs or 3 GCPs and still get a solution. And some of the errors that you could expect, or at least that we found in this paper, are shown here in the table. And so again, up here, if you have no knowns, then you need to solve for all 6 parameters, and you need at least those 4 GCPs. Roll would be, okay, let's assume the roll is 0. Then we can solve for these, and maybe only need 3 GCPs, and so on and so forth. Yes?
In that table of the knowns, so or is there uncertainty in the knowns?
There's probably some uncertainty in the knowns. Yes. Yeah. All right, other approaches to try to correct for geometry solutions. So this is an example of a data collect that Brittany and I actually did. These are example images from that collect. We spread our GCPs in the most glorious straight line you could possibly come up with on the beach, and then had to struggle with how to process these data. And
I'm sorry, I was just gonna say on a side note, we'll learn about that tomorrow, because like on the beach, they looked amazing.
yeah,
We thought we did a really good job. So we usually always like to do a test hover and then actually draw on where we want to put them, and then have someone walk out and do
Into
them.
those
Because it looked great on the ground.
yeah, we thought we were doing a great job when we were on the beach, and then the drone had a different idea, different perspective. Yeah. Okay. So one of the features that you can exploit to try to add additional information is the horizon. It can help you solve for both roll and tilt. So obviously, if your horizon is slightly angled, that's going to tell you something about the roll of your image. So you can try to use, you might use a feature detection to find that horizon line, and then you can look at the angle of that horizon line, or you can just click it if it's just one image. If it's a UAV or something that's changing through time, you might want to develop some sort of automated extraction of the horizon line. You can also use the horizon line to help correct for inaccurate tilts. And this turns out to be, inaccurate tilts or pitches turns out to be one of the biggest sources of errors that you can have in your data set for some of the advanced products like CBATHY or things like that. And why that is because your tilt is basically controlling, which I'll show you a little graphic of. So your tilt is controlling how far up or down the camera is looking. And so if you're putting that in inaccurately, then the whole surface that you're projecting, it can stretch your wavelengths too much or shorten them too much. And so if you're trying to measure wavelengths for something like CBATHY, and you have an incorrect tilt, then you can really skew a lot of your results. And that also goes through if you're trying to map out a sandbar along the coast or something like that, and your tilt is incorrect. It'll artificially shift the position of that sandbar onshore or offshore.
Is there like a back of the envelope, like degree to meter that you might?
So it all depends like on your camera setup and your camera geometry. We have an example coming up where I can show you a degree of pitch, or we were off by 1 degree in tilt and what that did to our CBATHY results. But it's going to change depending upon your camera, your lens, your whole setup, all of those parameters. Let's see, your shoreline, you could also use a feature like your shoreline, or if you have a pier that you could see and you know the angle of your shoreline or the angle of that pier, you could use that to help better define azimuth as well. So these are things that are not programmed into the toolbox right now, but these are little tricks that you can use and investigate if you find yourself getting some poor solutions to some of these geometries. And you know, I think that's something we'd love to include in the future in the toolbox, is the ability to do some of these things, but it's not there yet. And if somebody's really passionate about adding these features to the toolbox, we welcome crowdsourced participation and code development to integrate in. So this is just an example. This is, again, this image is from I believe the paper that was referenced earlier, that 2016 paper. So on the left is what we're calling the 6 degree of freedom solution. So that's where we're using 4-fold GCPs. This is taken here at the FRF. This is in local coordinates. Our local coordinate system here at the FRF is aligned with the FRF pier. So you can see in this image on the left, the pier is nice and straight going offshore. This image over here on the right is an example of using, I think, 1 GCP and the 2 degree of freedom solution, which is probably this one right here. And so that's what you got for the resulting geometry. And you can see that the azimuth is a little bit off. So the pier is sort of misaligned a little bit. You can, let's see, I think that's the biggest difference that you see here, is that our azimuth ended up a little bit off. And so your features may not plot exactly where you want them to be.
And the crab is moved on the top edge.
Oh, yes. Yes, you can see the crab is right here versus being right here. Thank you, Rob. I was looking for another feature I could point out that was different. So while you can get a solution with these reduced degrees of freedom, there are likely errors that are introduced. And so just be aware of that. And I think, yes, this was the worst case solution. And then that was our best case solution. So here's an example that gets to your question, Alex, that you asked earlier. So this is an example from the collect that I showed you that Brittany and I did, where the image on the left was using only those 4 GCPs. And then this image on the right was actually, we went in and we pulled the data from the UAS trajectory and used the shoreline and the horizon to help correct and solve for our azimuth, tilt, and roll. So the GPS information came from the UAS trajectory, and then azimuth, tilt, and roll came from iterating over the horizon and the shoreline position. And so if you zoom into this box, so now instead of plotting this as RGB values, we're just plotting it as pixel intensity values 0 to 1, and trying to highlight that these wavelengths are looking a lot different between these 2 pictures. And if you look up here in the table, the biggest difference in our extrinsic parameters is a 1 degree difference in pitch. So this one had a pitch of 78.32. This one had a pitch of 77.31. There were small, like 0.2 differences in roll, 0.1 difference in heading, but the pitch was really the biggest one, and the elevation of the camera also came out a little bit differently. And so if we go fast forward, we were running CBAFI on this video collected with this drone. And so these are the differences in bathymetry calculated with CBAFI from those 2 projections. So over here on the left, the red line was with the incorrect geometry. And then the blue was with the corrected geometry using those shoreline and horizon corrections, and it matched the truth, which is in yellow, much better. So that 1 degree difference in pitch and a few meters in the elevation of the camera made a really big difference in the quality of the final bathymetry data that we were getting out of CBATHY. So that's why it's really important to get this camera geometry correct, because we're generally looking at pretty low angles. We're looking out pretty far, 500 meters. And so small changes in angles result in large changes in horizontal distance.
So just to clarify what this means, it's not that an angle difference in pitch changes your error because you're just simply taking a different view of the feature. It's that your estimation of that 1 degree difference, you're not accounting for that 1 degree difference in the extrinsics, or if they were both perfectly calibrated, you would get similar errors.
So, all right, I think I understand your question. So we had, basically, you can think of it as these are two different solutions to where the camera was in space and how it was oriented that we got. So these are two different solutions using different input parameters. The difference between them was largely in the 1 degree in pitch and a couple meters in elevation. And what that did is that changed the projection of our image. So it stretched our pixels different amounts across the image, and that's exacerbated in the offshore portion of the image. And so one of these is much more correct than the other one is. And we know that because when we use CBATHY, which measures the speed that waves are moving and it's related to the wavelength of the waves, the speeds were basically way too slow for what the known depth was in the first solution. And in the second solution, it matched much better. So that told us that was a much better solution for the extrinsics.
But what happens in the shallow, very near shore region, and even on land, isn't so about if you are interested to shoreline position or features?
So the closer you are to the camera, the smaller these errors will be, right? So it's, projective geometry. So a tiny error in pitch close to you results in a tiny error in distance, but a tiny error in angle at far distance results in a much larger distance.
What is that? We are using, not in August, because this morning session, we saw that to get good information about some of the hydrodynamic processes, we're going to use an August station, not a sort of GoPro type camera. So if we use then a GoPro type camera to sort of understand maybe location or position of the shoreline due to the characteristics. What I understand from it is that this extrinsic sort of correction might not matter as much because we are looking at features that are much closer than things that. So basically for GoPro or production that was this morning, for basically standard cameras that are not Argus, it seems that less attention can be paid to this step.
As long as your camera is very, very close to what you are looking at. So you could take a trail camera and it might be mounted far away from where the shoreline is that you're looking at. And if your shoreline is at a position that's far from your trail camera, it's going to be really important to get the geometry of that trail camera correct, even though you only care about the shoreline, right? It has to do with the feature that you're looking at and its relative proximity to the position of your camera. Does that make sense?
Yeah. So if you want to look at basically take like a long shore and that's
then it matters. Yep.
But then the spreading of the GCP is also easier because you don't have to do it right.
Yep. But it can get hard to see GCPs at very far distances from your camera. So these are all there's all things that you have to weigh when you're designing your camera setup. How are we doing on time? There's 2 more questions. Do you want me to?
So we're 6 minutes over.
Okay. I'm going to keep moving forward, and if you guys could come find us afterwards for your questions. So what coordinate system to use? So again, the coordinates of your GCP will define the coordinate system of your extrinsics and thus of your final projected image that you're using. Again, you can use a geographical versus a local coordinate system. For a lot of the more advanced downstream CIRN products, things like CBATHY, we need to get the data into a local coordinate system. Some of the benefits of staying in a geographical coordinate system is it's super easy to overlay onto like Google Earth or something like that. Anyway, there's uses for both of these different coordinate systems. This is just giving you an example of a local and longshore cross-shore coordinate system we define here at the FRF. It's defined as a rigid transformation from a known world coordinate system. And typically the Z is the same for your two local coordinate systems, and it's just a translation and rotation about the Z axis to change the alignment of your X and Y axes. This just walks you through how to convert from a geographic and define a local coordinate system. This in the past has, I think, tripped a lot of people up, and Brittany has spent a lot of time of coding this functionality into the toolbox such that you can build and define your own local coordinate system on the fly within the toolbox. And these are the two functions that allow you to do that. And whether you're in a world or a local coordinate system, for the purposes of the toolbox and the nomenclature, like you can think of that as your world coordinate system. So you're going from world to camera, and world might be an actual geographic world coordinate system or a local coordinate system. All right, it's important not to mix those things. Don't mix your conventions between your local coordinate system and your geographic coordinate system for your rotation and your translation parameters. So pick a coordinate system and stay in it, and make sure you define your angles appropriately for that coordinate system. This is often a really big place that things get messed up, because if you input some of your guesses incorrectly into the nonlinear solver and you're mixing these coordinate systems, it's basically not going to find you a solution. All right, so what if my camera is moving on a UAV? While UAVs can hover in place, they aren't completely still, so we need to update our geometry for each frame. So these are two examples. On the top is taking a Timex in image space, so basically doing a time average at every pixel location of just your raw movie, and you can see how blurry the world looks, and that's on a stabilized gimbal camera. So that's, you know, it's trying to stabilize itself, but it's still moving. So this is the example Timex created after solving for a new geometry for each frame. And then this is an example transect across both. You can see all the features on land stay fixed through time, whereas here they're wiggling and moving all around. Okay. So we don't want to manually click GCPs for every frame in a movie collected from a UAV. So there are some automated feature recognition algorithms built into the toolbox. We tend to call these virtual GCPs, and the practicum will walk you through how to find them. So these are features that stay fixed and are always in every frame in your movie. So don't pick something on the edge that then by the end of the movie is out of your frame. These can be bright features or dark features, is that in there? They can be bright features or dark features relative to the pixels around them. And there's a little GUI that walks you through how to threshold for how bright and how dark. There are also more automated feature recognition algorithms that could be used for that, and that's not presently in the toolbox. It does exist. So Brittany has a nice GUI bathy version, which is more of a GUI that implements the function of the toolbox. And there is a automated feature recognition tracking algorithm in there that's not this manual process. So this is what you'll go through in the practicum. I'm going to speed through this because we're going to go over it in the practicum. But the idea is that you identify a search region that does allow for some intraframe movement. You then identify, this is showing a brightness threshold. So it finds all the pixels brighter than a certain intensity. It then does a center of mass calculation of those bright pixels to find the center. And it defines that center point as the UV coordinates for that virtual GCP. And then we know the elevation of that feature. And so we can use that to automatically solve your extrinsics for every frame. And so if you do that, you can then plot how your geometry has, or your extrinsics have varied through time. So these are the 6 parameters as a function through time from a hovering UAV that was just told to go hover in place. So you can see that, you know, the roll in this case wiggles around a little bit by a few degrees. So you can plot and look at how much your extrinsics are varying. This is just talking about some of the alternative approaches to stabilize. You could use automated feature matching. And I think Brittany gave some suggestions here of some of the functions she uses in the computer vision toolbox. And I think those are some of the ways that are implemented in GUI Bathy. All right, so in summary, extrinsic calibration solves the camera equation for position and pointing angles using known features in the field of view. You want at least 3 to 4 GCPs, more is better. You want to spread your GCPs out in both dimensions whenever possible. Can also use direct surveys of the camera position or information from the UAS trajectory file, as well as the shoreline and the horizon orientation if you can't get a good solution using the GCPs. You need to input an initial guess of these 6 parameters into the nonlinear solver to initialize, and those guesses need to be reasonable. So you don't want to mix your coordinate systems when inputting those guesses. For a UAS or a fixed station that might wobble, so a camera on a very skinny tower in a windy environment, or a camera that sees a lot of thermal expansion during the day, you need some sort of automated process to solve the geometry for each frame. And you can do that by using fixed recognizable features in the field of view.